Hi everybody, so today's note is about average rate of change. And this is the first lesson of this unit where we're going to get deeper into rates of change. And this is actually going to lay the groundwork for everything we learn in calculus for those of you who are taking it. So first I want you to just think about what average rate of change means to you, or even just rate of change. So what are some things that we measure rate of change in? So a classic one is kilometers per hour. That's the rate of change of speed. So let's think about why we use kilometers per hour. Well, it's just the number of kilometers that you travel in 1 hour. So it's the amount that your distance is changing with respect to a 1 unit change in time. In that case, we're measuring time in hours. Another common one is meters per second. That also can calculate speed. We can also think about, if we're looking at bacteria growth, the number of bacteria per hour. Or, if you're thinking about a tub draining, the number of liters per minute that is draining from a tub or some other container, things like that. So what do all of these units have in common? Well, first of all, it's something per something, so it's always two variables that have an effect on each other. But what's important to realize is that it's always the dependent variable divided by the independent variable. And the independent variable, when we say per hour or per minute, we're always looking at a 1 unit change in the independent variable. So the rate of change tells us how much does the dependent variable change with respect to a 1 unit change in the independent variable. So a positive rate of change means that dependent variable is increasing. A negative rate of change means that the dependent variable is decreasing. And a rate of change of 0 means that on average there's been no change at all. So if we take a look at this note, we can see that we will be defining average rate of change as I kind of just did, but we have the formal definition here. You're going to need to be able to represent average rate of change in words, numerically, graphically, and algebraically, and then be able to calculate and interpret average rate of change of functions arising from real-world applications. And you're going to need to be able to do that from a written description, from an equation, from a table of values, or from a graph. Okay, so be able to calculate the average rate of change from any of those. So the formal definition I have written there is there for you. In a relation, the change in the quantity given by the dependent variable divided by the corresponding change in quantity given by the independent variable. So let's take a look here over at GeoGebra. So here we have the graph of f at x equals x squared. And you'll notice that I created 2 points here, A and B. So if we want to look at the average rate of change between A and B, that would mean then the change in y divided by the change in x. Okay, and that would give us a unit. So where else have we seen change in y over change in x? Well, the change in y here, so that's the vertical change, that's the rise, divided by the horizontal change, that's the run. It's the same as slope. So if you take a look over here, I have the equation of this line in y equals mx plus b form. So if you take a look at the m, which is the slope, that is actually the same as the rate of change. So this line here is called a secant because it connects 2 points on the curve. Okay, so the slope of this secant is the average rate of change between these 2 points A and B. So this 3.04 means that on average, when going from A to B, the y values increase by 3.04 units for every 1 unit of x that you go over. So on average, every time you go over 1, you're going up 3.04. Okay, and that's again on average between A and B. So if A stays in the same place, but B goes further up the parabola, you'll notice that the average rate of change is increasing. Okay, and that's because the slope of the secant is getting steeper. So on average, between A and B, for every unit that you're going over 1 unit of x, you're actually going up further. Okay, because you've gone further up the parabola. So we can also have a negative rate of change. So that's if I put B over here, notice the slope of this secant is negative. The line, the secant, is sloping down. And that's because on average, when you're moving from point B to A, when you're going over 1 unit, you're going down in Y. So when you move to the right with X, 1 unit, on average in this case, you're going down 1.27 Y's. So that's why you have a negative rate of change in this case. Now, what would it take for this to be a zero, an average rate of change of 0? Well, it would have to be a horizontal line, okay, which would give you a slope of 0. So notice here between B and A, I can't get it quite perfect. There we go. Here you don't have a slope at all shown there, which means the slope is 0. So that means on average, between B and A, you don't actually move Y at all. Now, we can see that's not the case for each point. Like when we move from B to A, you're going down and then back up. But remember, this is average rate of change. So on average, the amount that we go down here is the same amount that we increase here. So that averages out to 0. So the average rate of change, or the slope of the secant, can be 0 if when you draw the secant between the 2 points, this results in a horizontal line. Okay, let's get back to the note here. Okay, so let's formalize that a bit here. So if you draw, a parabola here, just a nice normal parabola, boop-a-doop, doesn't have to look that fancy. And we have a starting point x here, okay? So we're going to call this point x1, the x value x1, and then the y value, using function notation, will just be f at x1. Okay, and then we're going to do a second point over here, and its x value will be x2, and its y value in function notation is just f at x2. Okay, so these 2 points represent any 2 points on the parabola. Okay, and we can draw a secant between them. So that just, oops, that's not what I want to do. Try it again. Just connect the 2 points. So there we go. So delta y, so the change in y divided by the change in x, is equal to f at x2 minus f at x1. Okay, so that means if you're looking here, the change in y is just this distance here. Okay, so f at x2 minus f at x1, that's the length of that line there. Divided by, I'll use a different color, and then we're talking about this distance here, so the change in x, that's just x2 minus x1. Okay, so this is just another way of writing this whole thing. It's just the slope of the secant. Okay, and that is how we determine the average rate of change. Okay, so really this is just the slope formula. It's just that now we're using function notation on top instead of y2. So in grade 9, we use y2 minus y1 over x2 minus x1. This is the same thing. It's just that we're using function notation, so f at x2 instead of y2. And we can say that the secant is a line connecting the 2 points. Okay, so the average rate of change on the interval from x1 to x2 is determined by this formula, which again is just the slope formula. Okay, the average rate of change is expressed using both units. So I spoke about this a little bit at the beginning. So things like meters per second, bacteria, per hour. What else do I have here? Dollars per person. You know, if you're looking at how much money you've made when selling something. But the key here is that it's always the dependent divided by the independent. Okay, so should be good at identifying which is which by now, since we've been working on that since grade 9. But that's the key to determining what your units will be. So if you are given the equation of a relation, you can calculate the average rate of change on a given interval using, again, the formula above. Okay, one more thing to note here is that if you are given a linear relation, okay, here's a linear relation, think about what is true about its rate of change. Okay, if you calculate the rate of change between, let's say, this point and this point, is that going to be any different than calculating the rate of change between, let's say, this point and this point? No. Okay, because a linear relation is just a line. So the slope is the same no matter where you choose the 2 points. So this means no matter what 2 points you're choosing, the rate of change will be the same. So we call that a constant rate of change. So a linear relation has a constant rate of change, which means that it's the same no matter where you find it. So if you are given the equation y equals mx plus b, it's just the m value, right? It's just the slope of that line. However, if you have a nonlinear relation, so something like x squared or like the sine curve or anything that's not linear, you're going to have what we call a variable rate of change. So let's say if I found the rate of change between these 2 red points here, and I did the slope of a secant, notice the slope of that secant is going to be very different than if I have this point here and this point over here, and I draw a secant between the 2 of them. Okay, so notice that over here, this secant, it has a positive slope. Okay, it's going to be a positive rate of change, and it's quite a positive, and it's quite steep, so it will have a higher value. Now over here, on this one, this will be a negative rate of change because it slopes down, and it will be, it's less steep, so it will have a smaller magnitude. Now, it's also possible, of course, as I showed you before, to find 2 points where when you draw the secant, you'd actually have an average rate of change of 0. So basically, we say that a nonlinear relation has a variable rate of change. So the average rate of change will differ greatly depending on where the 2 points are chosen. Okay, so it's a bit more work to do there. So here's our first example, just about a car rental company. It charges at C at D, so we can assume that where it says it's cost per day. Sorry, for the daily distance. So it's 15 cents times D, so 15 cents a kilometer, excuse me, plus $35. So $35 a day. So if we were to graph this, it's a linear relation. Okay, so we have, it would start at $35 a day here, and then it would increase by 15 cents a day into all eternity until the domain makes sense to end. So in this case, the farther you drive, the more you pay. Right? So if you are driving 100 kilometers, you're paying a lot more than if you only drive 5 kilometers. But the rate of that cost increase stays the same. So the amount that your cost is changing by every kilometer stays the same no matter how many kilometers you drive. So that means that it's a constant rate of change. So it is always increasing by 15 cents per kilometer. Okay, so this is a constant rate of change of 0.15, which again, we can see that that's m in the formula, and that would also be equivalent to the slope of this line. Okay. Example 2. Andrew drains water from a tub which holds 1,600 liters of water. It takes 2 hours to drain completely. The volume is graphed below. So I'm going to graph this for you here. Okay, so this information would be given to you. So we're going to increase each, let me just see here, by 2. So I'm going to label every other one as 4. So here's 4, 8, 12, 16. Okay, those are the liters. And that's in hundreds of liters. So volume in hundreds of liters. Okay, and then we have our minutes on the independent axis here. So we're going to go up by 40 minutes, I believe. Trying to read my own writing. No, we're going up by 10. So this is 20, 40, 60, 80, 100, and then 120. Okay, so the points that were given are 0, 1600, or 0, 16, because it starts with 1600 liters of water. Okay, then 20, sorry, I'll label it 1600. Then 20, 1, 1, 1, 1, as weird as that is. So about here. 20, 1, 1, 1, 1. Okay. 40, 7, 11. 60, 400. 80, 178. And at 120, we're at nothing there. So it takes 120 minutes to drain, which is crazy, but okay. All right, so we can connect a smooth curve here. Hopefully yours is a bit smoother than mine here on the tablet. Okay, so this is there, some exponential decay. So let's take a look and think about the average rate of change of this. Okay, the average rate of change between any of these 2 points is going to be negative, first of all. I know that because we're comparing volume to minutes. And as a tub is being drained, the volume is going to be decreasing. Okay, so I can think about that logically. Then I can also think, well, no matter where I draw a secant line, that line will be sloping down. So my slope will be negative. Okay, but depending which 2 points I choose, it could be a higher magnitude number or a lower magnitude, okay? So on average, from 0 all the way down to 120, it takes 1,600 liters are drained in 120 minutes, okay? But that's not what the question is asking for. It's wanting us to look between these specific intervals, okay? And so the reason that we're doing this is to practice using the function notation properly and to be able to compare the difference. So the first is between time of 20 and time of 80. So that's between this point, I'll use a different color, between this point and this point. Okay, so this is question I. Okay, so we're going to call it average rate of change. We write it as delta V over delta T. So change in volume over change in time equals, okay, and so we're going to do then, that's going to be F at 80 minus F at 20 divided by 80 minus 20. Okay, so it's this one minus this one. So F at 80 is 178, and F at 20 is 1,111. Divided by 80 minus 20 is 60. So when you put this in your calculator, you get negative 13.33. Okay, now we need to put the units. So it's liters per minute. So this negative means then that the volume is decreasing, okay, at an average rate of 13.33 liters per minute between 20 and 80 minutes. Okay, now I want you to take a close look at how I answered this question because there's a few areas for error that people make. So first of all, it's crucial that you use the word decreasing in your answer. I'm looking for that you're interpreting the negative to mean that the volume is decreasing. I'm also looking that you're not putting a negative in front of the 13.33 in the sentence. Okay, because using the word decreasing has already taken care of explaining why that negative is there. If you say it's decreasing by a rate of negative 13.33, technically that's a double negative and that doesn't actually make sense. Okay, so I'm really looking for you that you're interpreting this number properly. Okay, and I'm also looking that you're using the word average in your sentence and showing me that this is between 20 and 80 minutes and that in this case it's not the average of the entire time. Okay, so I want you to use this knowledge to try to do the exact same thing between 40 and 80 seconds, okay, using the same notation, and between 100 and 120 seconds. So the answers you should get are, for the second one, okay, you should get minus 15.55 liters per minute. And for the last one, you should get minus 2.2 liters per minute. Okay, now I want you specifically to think about this one, why it makes sense that this number is so much different than this number. Why are we only at minus 2.2 when this one was at minus 15.55? Okay, and we can discuss that more together as a group tomorrow. But understanding the difference between these two is crucial. So if you don't understand that right now, make sure you put a big star by it and make sure you talk to me tomorrow. Okay, example 3. So this is the case where, so the very first question we were just given the formula, but it was a linear. The second one we were given a graph, or we could have just looked at the coordinates, kind of thinking about it as a table of values. In this case, we're just given the equation of this parabola, so you're going to be expected to know how to do this as well. So it wants us to create, calculate the average rate of change between 0 and 1, 1 and 2, 2 and 3, 3 and 4, and then just using those average rates of change, discuss what we think is happening with this rock. Okay, so it's kind of different because we're not looking at the height, we're looking at how on average the height is changing with respect to time. So notice that this is a downward facing parabola, okay. Its y-intercept or its h-intercept is at 120. So we can kind of start thinking about what this is actually going to look like. Okay, let's go and do this. So first we have delta h over delta t. So notice it's the dependent over the independent. So that's going to be h at 1 minus h at 0 all over 1 minus 0. So to find h at 1, we actually have to put 1 into the formula. So minus 5 times 1 squared plus 10 times 1 plus 120. Okay, so that's h at 1 minus h at 0. So we know that that's 120 because when we put 0 into this, we'll get 0 plus 0 and then 120 divided by just 1. So when we do this, we get 125 minus 120 over 1. So we get 5, and the units are meters per second. Okay, so that means between 0 and 1 seconds, it's on average, increasing, the height of the rock is increasing by 5 meters per second. So let's think about that. So this is 1 second. That means from here to here, on average, we're increasing our height. Okay, so now let's do the second one here. So between 2 and 1. So delta H over delta T is equal to H at 2 minus H at 1 divided by 2 minus 1. Okay, so if you put 2 into the equation, you get 120 minus, and then 1 is 125 over 1. So this is actually negative 5 meters per second. So this negative means that between 1 and 2 seconds, on average, it's decreasing, but at the exact same rate that this was increasing. So this should be a mirror image to this because it's decreasing by 5 meters per second. Okay. Now we'll do this third one here between 2 and 3. So H at 3 minus H at 2, all over 3 minus 2. So in this case, you get, if you put 3 into the function, you would get 105. And then if you put 2 in, you would get 120. So here we actually have negative 15 meters per second. So that means between 2 and 3 seconds, it's decreasing by quite a bit more. It's quite a bit steeper. Okay? And then you can imagine what's going to happen between 3 and 4 seconds. Okay? So what's your prediction? What do you think is going to happen? How is delta H over delta T between 3 and 4 going to differ from this minus 15? What makes the most sense? You could kind of make a guess at what you think it might be. Is it going to be negative? Is it going to be bigger or smaller than this? That's what I want you to think about. So when you put this in, you get 80 minus 105. So you get negative 25 meters per second, which makes sense because the height should be decreasing faster and faster as it hits the ground. It goes, okay, that was terrible. Let's not do that. Okay, so I need to just create a whole new graph. Basically what happens here is that it's going to go up and down, and then it's going to go down faster, 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 faster. Okay? So it asks us to discuss the results. So I've been doing that orally, but let me just write something so you have something more formalized in your note. So the rate of change here represents the speed of the rock, right? Because the units are meters per second. So when in doubt, just kind of look at, okay, well, what's my dependent divided by my independent? What does that mean? Well, meters per second, that's speed, right? So therefore, when rate of change is positive, the rock is rising, okay? Because that means that height is increasing with respect to time. And when negative, the rock is falling. Okay? Because think about it, because that means height is decreasing with respect to time. So from 0 to 1 seconds, the rock climbs, or actually don't say climbs, say rises to its max height at 1 second. Then starts falling and falls faster and faster until it hits the ground. there you go. So notice that I talked about whether it was falling, so that's positive. Sorry, falling, rising is positive rate of change, and falling is negative rate of change, okay? So as a result of this note today, you should be able to define average rate of change as the slope of a secant between 2 points. You should also be able to discuss the difference between finding the average rate of change in linear relations and nonlinear relations. You should be able to find the average rate of change given an equation using function notation or a table of values or a graph. Okay, any of these things actually. And then once you have the rate of change, this is crucial. You need to be able to interpret it within the real life context, including if the rate of change is negative. Okay, so that's our note for today on average rate of change. Thanks for watching, guys. Hope you learned lots.